Hey Geometry 2 students, Ms. Craft here. Today we're going to be looking at 11.2 notes, which is proving figures are similar using transformations. And we do have one vocab word to start, and that's a similarity transformation, which is a composition of transformations that maps the pre-image to the image by translating, reflecting, rotating, and or dilating. So in Geometry 1, you learned about congruence transformations, which is a composition of transformations using only translations, reflections, and rotations. So today we're going to be adding dilations, and that is figures are similar. So remember all those things that it keeps from 11.1. Betweenness, lines are parallel, things like that. Okay, but the size is not the same. So our first example, we're going to be describing similarity transformations, and all that means is you have to be able to look at an image and figure out how you got from one figure to the next. Okay, this one, the first one I'm moving from triangle LMN to triangle STR. So what I noticed first is that triangle LMN had to be rotated in order for it to be the same direction as triangle STR. And I know that it's a 90-degree clockwise rotation. Okay, so when I transform triangle LMN 90 degrees clockwise, I did not write the points here, but if you want to, you can. You can show where triangle L prime, M prime, N prime would end up, but I don't feel the need to. Okay, so once I rotate clockwise, I'm in quadrant 1. And then I know that it has to be dilated because these figures are not the same shape, the same size. So I have to figure out how many times did triangle LMN get multiplied, basically, to become triangle STR. The way that I do that is I look for a straight line, which you can also use the distance formula if there is not a straight line. But here, conveniently, I have segment MN, which is 2 spaces. Okay, so a length of 2 for MN. And I'm going to go to its corresponding part. I know based on the naming that MN corresponds to TR, so I'm going to look at TR in my second triangle and I'm going to count that. So TR is 1, 2, 3, 4 spaces. And remember from 11.1 we do image over pre-image, so 4 over 2 gives me a scale factor of 2, so that's where I got the second part from. Okay, the second example, I have quadrilateral RSTU, and that's going to quadrilateral XWZY. Please note that we do not always write things in alphabetical order. It must be written so that your corresponding parts match up. So that means point R corresponds to X, point S corresponds to point W, and so on and so forth. Okay, that's important for you to be able to identify basically corresponding segments and angles, which we will get to in later lessons. Okay, so going from RSTU to XWZY, I notice first that it's a reflection. Now, the line is not a neat line. What I mean by that is it didn't get reflected over the y-axis and it did not get reflected over the x-axis. It's also not on a whole number. And I know that because the way that I find this is I go to my image, so point Z, based on the naming, corresponds to point T. So I'm going to figure out how many spaces between the two. So from Z to T is 1, 2, 3 spaces. Because a reflection has to be an equal distance from one figure to the other, I'm going to divide that by 2. So 3 divided by 2 is 1.5. Okay, so then from point Z, I'm going to go 1.5 spaces. 1.5 puts me at -1/2. And so the line of reflection is x equals -1/2. That's where I got that from. Okay, so once I reflect RSTU over the line x equals -1/2, that figure ends up in quadrant 1. And again, you can draw R prime, S prime, T prime, U prime if you so choose, but I do not draw that middle transformation that occurs. Okay, then I notice that it's a translation because these are not mapped onto each other. So once I reflect this over the line equals 1/2, T ends up where W is, and point T does not correspond to point W. So I'm going to translate this figure down 1 unit. I used vector notation here, so just basically in your like less than, greater than symbols, 0, -1, saying that it translates down 1 unit. Okay, then I notice that it's a dilation. The dilation I'm going to use would be from point T now that I've translated it. So point T now maps to point Z. And again, I'm just going to do what I did on the first example. I'm going to count a segment. So I notice here ST is 2 spaces, and ST corresponds to WZ, and that's 1 space. Remember that it has to be image over pre-image, so I'm going to do 1 over 2. It doesn't need to be reduced, so that's how I get a scale factor of 1/2, which tells me it's a reduction, not an enlargement. Okay, so then I left 2 incomplete here so that you can practice those if you would like, and I would recommend that you do because obviously it's probably going to be on your quizzes and exams, so make sure you know how to identify similarity transformations. Okay. All right, determining if something is similar, congruent, or neither is basically identifying what transformations occurred and if there was a dilation and if that dilation occurred the same for both variables. Okay, so for this first example here, I have a translation moving 3 to the right and 4 down, and then a rotation of 270 degrees. Congruence transformations are translations, rotations, and reflections. So because all I did was translate and rotate, I know that these figures are congruent because translations and rotations are rigid motions, which means it preserves size. Okay, my next example, I have x, y, like coordinate, to negative yx. You have to be able to identify what these notations mean. And that is the notation for a rotation of 270 degrees. Okay, then followed by xy going to 3x, 3y. This is a k value, 3 and 3, the same k value, being multiplied by x and y. So I know that this is a dilation, and because dilations do not preserve size, it has to be a similarity transformation. So these figures are similar because it was a rotation of 270 degrees and then a dilation by a scale factor of 3. Okay, the next example here, I have my figure being dilated. Again, I have numbers right in front of x and y being multiplied by x and y. 1/2 times x and 2 times y. Because those are not the same k value, it's not the same scale factor, these are not similar. Okay, they can't be congruent because I'm changing the size, but they aren't similar either because I'm changing the size differently for x's and y's. Okay, so then what follows is irrelevant, a reflection or not. I already changed the size differently for both coordinates. So if it's not dilated by the same scale factor, then it can't be similar. Okay, so I left 1 here for you to do so that you can complete that if you so choose. Again, totally optional and not required. Okay, last thing here is something that AZ Merit really loves, and that's proving the circle similarity theorem. And that just says all circles are similar. We will get to circles later this semester, but for some reason, similarity of circles occurs prior to you knowing, I guess, important information about circles. So I just wrote some steps here, kind of like a proof, but not really. The first thing that we would do is, I'm sorry I didn't put it here, but if I'm transforming figure A to get to figure B, I need to figure out how to map B to A. Okay, circle B, that's what this means here. You notate circle with literally a circle with the dot in the middle. And then a circle is labeled by its center. So because this is a center B, that's why it's called circle B. Okay, so the first thing I'm going to do is translate or move circle B so that point B maps to point A. Generally, you would notate this with a vector, but I'm not sure how many of you learned vectors, so you could also see it that way. Translating circle B along vector BA is how it would be noted. Okay, the second step is I'm going to dilate circle B prime, and it is B prime because now I've transformed it. And my center of dilation is going to be point A because now they map to each other. B and A are the same point. And my scale factor is R sub 2 over R sub 1. Okay, that's because I'm moving from B to A. So A is my second figure. Finally, because the transformation maps all of the points from circle B to circle A, meaning once I've dilated This circle will be exactly the same as circle A. That means that circle A is similar to circle B. Okay, every single proof for these is the same. All I've done here is change the naming of the radius for each one, and obviously the sizes are different, so if you wanted to rewrite this using this second example here, you could. But that's all I have for you for 11.2. So if you have any questions again, please send me a message. Thanks.